In the last lecture, we were examining unidirectional transport in a finite domain. Okay. So, the configuration consisted of two surfaces, z direction perpendicular. Okay. Bottom surface is at z is equal to 0, top surface is at z is equal to h, top surface is at t is equal to t infinity, bottom surface is at t is equal to t naught, and the medium in between, right, t is equal to t infinity at initial time. Okay, t is equal to t infinity at initial time. So, that was the configuration. So, what you would expect is that the temperature profile as a function of time initially is just equal to t infinity. Okay, so, let me shift this a little further away. Okay. Okay. In the long time limit, it has to be a linear profile between t infinity and t naught. Okay. And it reaches this by a series of profiles in which the temperature at the bottom surface first increases and then slowly that increase spreads upward until you get a linear profile in the long time limit. Okay. So, this was the configuration. Okay. And if you recall, we had scaled t star is equal to t minus t infinity by t naught minus t infinity. Okay. So, that this is t star equal to 0, bottom surface t star equals 1, and this is temperature is 0 throughout the domain at initial time. Okay. And we had scaled z is equal to z star is equal to z by h, okay, which means that this is z star equals 1 and this is z star equals 0. And the scaling for the time was t star is equal to alpha t by h square. Okay. You can consider t alpha by h square as, or rather h square by alpha as a diffusion time. Okay. So, h square by alpha has dimensions of length square divided by length square by time. So, this is something like a diffusion time across a distance h. Okay. So, that is what the time scale is scaled by. Okay. And once we do this, we found that the equation was of the form partial t by partial t is equal to d square t by dz square. Okay. And the boundary conditions t star is equal to 0 at z star equals 1, t star is equal to 1 at z star equal to 0, and there was one initial condition, that is that t star is equal to 0 over the entire medium between 0 and h, that is for 0 less than z star less than or equal to h at t star equal to 0. Okay. So, that initial time, the temperature throughout the domain except at the bottom surface is equal to 0. Okay. So, that is what we started off with. Procedure for solving this: t star was written as a steady plus a transient part. The steady part was just the linear profile, if you recall. The steady part was the linear profile that satisfied the boundary conditions. T star is equal to 1 at z star equals 0 and t star is equal to 0 at z star is equal to 1. So, this satisfied the boundary conditions. Now, therefore, the equation for the transient part, okay, partial of T t plus T s by partial t is equal to partial square of transient plus the steady by partial z star square. The steady part does not depend upon time, okay, and the transient part, this equation we had solved was that d square t steady by dz square is equal to 0. That was the equation we solved for the steady part, which gave us the linear profile. Okay. Therefore, this term also goes away, and the equation for the transient part just reduces to partial of transient by partial t Okay, so that was the equation for the transient part. What about the boundary conditions? At z star is equal to 0, t star is equal to 1, that was at the bottom surface. However, we know that the steady part is also equal to 1 at the bottom surface. Okay, the steady temperature is also equal to 1 for the linear profile. Okay. Therefore, the temperature for the transient temperature has to be equal to 0. Okay. At z star is equal to 1, the total temperature is 0 and the steady temperature is also equal to 0. The total temperature is 0 and the steady temperature is also 0, which means that the transient temperature is also 0. Okay. Important point to note, boundary conditions are homogeneous for the transient part. They are both 0 at both the boundaries. The initial condition, okay, at t star is equal to 0, t star is equal to 0, okay, for all z, okay, greater than 0. Okay. The temperature is 0 throughout the domain. The steady temperature is equal to 1 minus z star. Okay. Total temperature is 0, steady temperature is 1 minus z star because it is independent of time, okay, which means that the transient temperature has to be equal to minus of 1 minus z star. Okay. So, that has to be the transient temperature at initial time. So, again the total temperature is 0 at initial time throughout the medium except at the bottom surface when the heating has just started. Steady temperature is 1 minus z star, therefore, the transient temperature is minus 1 minus z star. Note that this is inhomogeneous. Okay. This is inhomogeneous and therefore, you have a transient temperature. If all boundary conditions in initial conditions were homogeneous, the trivial solution would just be that equal to that the transient temperature is equal to 0. So, therefore, there is driving at initial time. Okay. There is driving at initial time for this transient part. Okay. Now, separation of variables. Okay. The transient part of the temperature is equal to some function of time times some function of z. Substitute into the governing equation, divide throughout by g times z to get an equation 1 by g dg by dt is equal to 1 by z d square z by dz star square. There should be a star in both. Okay. That is the governing equation, and we had said that is you take the governing equation, substitute the transient temperature is g times z, divide throughout by g and z, okay, and this is what you get. Left side is only a function of time, right side is only a function of z star. Okay. Left side is only a function of time, right side is only a function of z star, and therefore, both the left and the right sides have to be equal to a constant. Okay. Both left and right sides have to be equal to a constant. Should that constant be positive or negative? So, to check that, we can take just the left side 1 by g dg by dt star is equal to some constant k. If this constant is positive, then g is increasing exponentially in time, whereas if this constant is negative, g is decreasing exponentially in time. For this system, we require that the temperature, transient part of the temperature has to go to 0 as time goes to infinity, so that the temperature becomes the same as the steady temperature. That means that this constant has to be negative, so that g decreases exponentially as time goes to infinity. Okay. So, this one, so this is equal to some negative constant, I had written that as minus beta square. So, then I solved for the spatial part z d square z by dz star square is equal to minus beta square, which implies that z is equal to a cos sine of beta z star plus b cos of beta z star. Okay. The boundary conditions in the spatial coordinate. Okay. at z star is equal to 0, t transient is equal to 0, which implies basically that z is equal to 0, because that is the only part that is dependent upon position. Okay. And in this equation, the sine function is 0, the cos function is 1. Therefore, this implies that b equal to 0, and at z star is equal to 1, the transient part is also equal to 0, which means that a sine of beta, this is equal to 0. Of course, if a is equal to 0, there is no solution. Okay. So, the only solution is if sine of beta is equal to 0. Okay. If a is equal to 0, then you just get 0 everywhere. Okay. It is a trivial solution. It does not satisfy the initial condition. Okay. The initial condition is non-homogeneous. Therefore, the only solution is if I write beta is equal to I into pi, where I is an integer. So, sine 0 is 0, sine pi is 0, sine 2 pi is 0, and so on. Okay. So, for any integer I, this sine of beta is equal to 0. So, beta can have multiple values. Okay. I will call that as beta I. Okay. It can have multiple values, that is all values of I pi for I being an integer. So, therefore, I get z is equal to a sine of I pi z star, and the g function I had got quite easily as e power minus I pi the whole square t star. Therefore, the transient part was equal to a sine of I pi z star e power minus I pi the whole square t star. This satisfies the equation and the two boundary conditions for any value of I. Okay, for any value of I. Okay. Therefore, the most general solution is one where I take all possible values of I, okay, and this coefficient is a I. And now, this has to be the coefficients a I have to be satisfied from the initial condition. Okay. At t star is equal to 0, t transient is equal to minus of 1 minus z star. Okay. Therefore, I get summation over I is equal to 0 to infinity of a I sine I pi z star. Okay. The exponential just becomes equal to 1 at t equal to 0. Okay. So, this is equal to minus of 1 minus z star. I should note that the limit of integration in this case can be taken either from 0 to infinity or 1 to infinity, because for 0 it just becomes 0. Okay. So, it does not matter. Okay. So, I can take it as well from 1 to infinity. Okay. So, this equation has to be solved for these infinite number of coefficients a I in this case, okay, for these infinite number of coefficients a I in this case. Okay. The solution procedure is what is called the orthogonality relation. Okay, it is called the orthogonality relation. Okay. If I take this function sine of I pi z star, okay, times another function sine of j pi z star, okay, and integrate over z between 0 and 1. This has the property that it is an orthogonal function. Okay. So, how do you see this? The sine, so I can write the product of sines as integral dz star between 0 to 1 cos of I minus j pi z star, okay, minus cos of I plus j pi z star. Okay. So, that is the integral. Okay. That is just using there should be a factor of half here. Okay. Okay. Sin a sin b is equal to half cos of a minus b minus cos of a plus b. Okay. So, that is, I can do the integral. Okay. So, I get half, okay, sin of I minus j pi z star by I minus j pi minus sine of I plus j pi z star by I plus j into pi, all integrated from 0 to 1. And you can easily verify that integer I and integer j, okay, at 0 this is all equal to 0, the entire term is equal to 0. At 1 also, if integer I and integer j, then this is equal to 0. Okay. This is equal to 0 for if I is not equal to j. Okay. If I and j are integers and if I is not equal to j, then this entire integral is equal to 0. Okay. This is the product of these sine functions. Okay. If I is equal to j, then I have integral 0 to 1 dz, okay, sine square of I pi z star, okay, is equal to integral 0 to 1 dz star into 1 minus half of 1 minus cos of 2 I pi z star. Integral of that cos function is a sine function and that is also equal to 0. Okay. However, the first term integral 0 to 1 of 1 by 2, okay, this is just equal to 1 by 2. Okay. So, this integral, okay, of two functions with two different I and j, right, this can be written as this can be written as 1 by 2 delta I j, okay, 1 by 2 delta I j. This delta I j is called the Kronecker delta. Okay, to distinguish it from the Dirac delta function that we had used earlier. Okay. So, this is equal to 1 by 2 for I is equal to j and is equal to 0 for I not equal to j. So, this can be used for implementing this relation. Okay. This can be used for implementing this relation as follows. Okay. This orthogonality relation, okay, can be used for implementing this initial condition. Okay. So, I have a I, okay, sine I pi z star, okay, summation over all I is equal to 0 or 1 to infinity, it does not matter, is equal to minus of 1 minus z star. And what I can do is that I can multiply both the left and the right hand sides by sine of j pi z star. Okay. So, okay, multiply the right and the left sides by sine of j pi z. Okay. Okay. And I can integrate on the right and the left sides between 0 and 1. Okay. Note that the right side is only a function of the index j, the left side is a summation over I as well. Okay. And using this relationship, right, the left hand side can be written as summation of a I into 1 by 2 delta I j. Okay. 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 Because this, okay, sine I pi z times sine j pi z integrated over dz just gives me 1 by 2 times delta I j, where delta I j is 1 if I is equal to j and it is equal to 0 otherwise. Okay. And on the right side you can do this integration by parts, okay, as a function of j. I will not go through the details, okay, it is just a straightforward integration. You have to basically use integration by parts, where you first differentiate 1 minus z star, integrate sine j pi z star, okay, and then get the second term and do the integration by parts. Okay. So, it is quite simple. The final result you get is minus 1 by j pi. On the left side I have I is equal to 1 to infinity of ai times 1 by 2 times delta ij. This is equal to, this is a non-zero only when I is equal to j. Okay. Therefore, the left hand side just reduces to aj into 1 by 2, which implies that aj is equal to minus 2 by j pi, which implies that aj is equal to minus 2 by j pi. Okay. Therefore, the transient part of the temperature field is equal to summation 1 to infinity, okay, of minus 2 by I pi. Aj is minus 2 by j pi, means ai is minus 2 by I pi, okay, into sine of I pi z star e power minus I pi the whole square t star. Okay. So, that is the solution for the transient part. The total solution is equal to the steady solution plus the transient solution. Okay, so, that is going to be the total solution for the temperature field. Okay. This summation is an infinite summation, of course, but you can get analytical approximations for a finite set of terms. Okay. You can get analytical approximations by including only a finite set of terms, okay, in the expansion. As t increases, right, this part goes exponentially decreasing with I square. Okay. Therefore, this part, the higher and higher terms become smaller as t increases. Okay. So, you can, for example, plot, okay, if you include, let us say at okay, the temperature field T star versus Z star. Okay. This is 0, this is 1 and this is 1. Okay. The final steady temperature is a linear profile. Okay. But at early times, right, if you include, let us say about 20 terms in this solution, you will get a solution that is fairly accurate. Okay. You will get solutions that go something like this. Okay. Okay. However, if you include too few terms in this expansion, let us say at t star is equal to 0.01 and include I is equal to 1 to 3, for example, okay, you will get a solution that is spurious that actually goes negative. Okay. And this is unphysical, okay, and it goes negative because you have this sinusoidal term here, okay, and this is unphysical. So, at relatively early times you make errors if you include too few terms in the expansion. So, you have to include a sufficient number of terms such that you get a converged series, okay, in this case. Whereas, at later times at t star is equal to 0.3 and 0.1, you get solutions that are fairly accurate, okay, including just a small number of terms in the expansion. Okay. So, this is the solution obtained using the separation of variables procedure. Okay. So, just to recap, okay, we had unsteady problem in the finite domain. We scaled temperature the usual way and we scaled z by the height and we got a natural scaling for the time, okay, as alpha by h square. Expressed in terms of this, the temperature field, the equation for the temperature and the boundary conditions end up being parameter free, they do not depend on any parameters. Okay. We separated the temperature into a steady plus a transient part. Steady part is a linear profile if the conductivity or the diffusivity is a constant, okay, 1 minus z star. Okay. The transient part, the equation for the transient part, this is important. It contains homogeneous boundary conditions in the spatial coordinates. Okay. The transient part of the temperature is 0 at both boundaries, it is non-zero at initial time. Okay. Because it is 0 at both boundaries, right, we were able to express this as the sum of sine and cosine functions, okay, and these what are called eigenvalues. Okay. These were discrete. Okay. You had discrete sets of parameters beta for which both the boundary conditions were satisfied. So, these eigenvalues were discrete, okay, because we had homogeneous boundary conditions on both surfaces. If you do not have homogeneous boundary conditions, then you cannot get discrete eigenvalues. Okay. So, we wrote this as the sum over all these basis functions, these discrete eigenfunctions sin I pi z star times e power minus I pi the whole square t star times coefficients. Those coefficients were evaluated using the property that these are orthogonal. That is, if I multiply two of these functions sin I pi z star times sin j pi z star, integrate from 0 to 1, I get something that is 0 if I is not equal to j, and it is non-zero only if I is equal to j. Okay. It is 0 if I is not equal to j, and it is non-zero only if I is equal to j. This was represented using the Kronecker delta function, where delta ij is 1 for I equal to j and it is 0 for I not equal to j. Based upon this, we were able to evaluate all of the constants in the equation, okay, all of the constants in this function, and get the temperature profile. This is an infinite series. However, we can truncate it and get a finite solution, which is a good approximation to the actual solution. The more number of terms in the series that you take, you will get a better approximation. Okay. For at late times, for t greater than 0.1 or so, you need only about 1 to 3 terms in the approximation. At very early times, you need a larger number of terms in the approximation. Okay. So, that is the summary of solution using separation of variables. This was in a Cartesian coordinate system. Okay. In the next class, I will extend this to a cylindrical coordinate system. Okay. So, I will continue this in the next lecture. I will see you then.